So then we talked about accuracy and precision. So accuracy is a measure of how close you are to an accepted answer, and precision is how close your measurements are to each other. So with accuracy, if you look at these bullseyes, we love to use bullseyes as an example. You would say the most accurate of these samples, the things closest to an accepted answer or the bullseye, would be C, right? So C here is the most accurate. And if you had to choose the next one, which was most accurate, you would choose hopefully A as the second most, because those are all pretty much well into the bullseye, if not all in the exact same place. And then if I asked you which two are the most precise, not accurate, but precise, the closest in coupling, again, I hope you would say C, but this time you would realize that B, that these are pretty well grouped together, and that those are the most precise. And then D is neither accurate nor precise. But the nice thing about precision, we talked about, if you're a field goal kicker, and every time you kick a field goal, so here's the uprights, and every time you kick a field goal, it kind of goes off this way here. Then if you consistently hit it that way, then we just have to move you a little bit this way, right? You move the kicker a little bit to the left, and then the feeling is if he stays with his precision, then he'll start getting it right into the field goal. All right, so that's accuracy and precision. Error in measurement. When we're working on laboratory equipment, which we did, and you did that wonderful POGL, which is posted online if you want to try that, if you missed it for any reason. But it helped us understand that we're limited by the accuracy of the tools we use. And so here is a tool that has measurements on it. We'll call it these units because that's what Team Umizoomi does. And what you can see here is that we know the leaf falls between 3 and 4. So we can do everything that we can measure for certain and then estimate one digit past what we can read. So we know this is 3. So the value of this is 3. And then because we can kind of see that this is falling somewhere between 3 and 4, we can say with confidence it's not 3.1. We could say with confidence it's not 3.9. Now, what we would say after that gets a little up for debate, but that's fine. That's what estimate means. So the user will estimate. So you knew the 3 and you're going to estimate this to be 0.5, I guess, is what I would do because I've already successfully drawn a 5. So anyway, 3.5 is what we would say for this. You could say 3.4, you could say 3.6, you could say 3 point whatever, as long as, right, we're pretty sure 3.9 is out of it, and we're pretty sure 3.1 is out. And, after that, it starts falling on debate. So that is that. And, why you have to measure a leaf this accurately, I joked it was Adam and Eve's Taylor. Okay, so it gets a little hairier for old eyes like mine to figure out here, but for certain the 8, and for certain 0.1, 0.2. This kind of looks like it goes a little bit beyond 0.2. That's not the straightest line, but even with that little crook there, you can see it goes a little beyond 0.2. So we can say for certain the 8. We can say for certain probably the 2. And then after that, you're estimating. So you would estimate maybe, 4, I don't know, 8.24. Again, not going to knock anyone off. So the estimated digit is known as a significant figure, as are the ones you know. So what does that mean, Mr. Roach? Well, this is what that means. Well, no, let's get into this. So here is an example similar to what we did on the POGL. So if we're using this measurement, and I know this drives Connor nuts that this is not lined up perfectly. So it's the angle. I'm telling you, it's the angle. All right. So you can figure out that it's somewhere between, that should be a 0. Anyway, it's somewhere between 1 and 10, I guess. Where's my little cursor? But anyway, it's between 1 and 10. So you can estimate, it's less than 10, but greater than 1. And if you had a guess, you would estimate that guess, right? So this here, you're estimating already. So that means you only use one significant figure, and you would say, I think that's about 8. Maybe you think it's 9, maybe you think it's 7, but you would have one estimate for that. For this one, now we know it's certainly 8, so we're not estimating that. So that's one significant figure, the 8. Look at that 8. And then the second significant figure you're estimating. And so you would say that's about 8 point, maybe 8, I guess, 8.8. So 8.8. So this is known, that's significant, and this is estimated. And if I want to stay consistent, I can circle the known like we did in the Bogle. Circle the known and align the estimate. All right. So then, oh, that's ruler. That's not 0. Oh, look at that. That's ruler 1. That's ruler 2. And then ruler 3, where you have more hash marks, you can see this is almost lined up perfectly at 8.8. So you could say the 8 for certain. You could, if you wanted to, say 0.8. You could say that's not quite a 0.8. So maybe you want to say 7.9. But I'm going to say 0.8. And then I'm going to say 0, 0.880. That's what I'm going to say, where that is an 8. Let's make that an 8. Does that look more like an 8? I don't know. All right. So it's everything you know. In this case, 8.8, and then 1 you estimate. So I know these, and then I estimated that. So that has 3 significant figures. So what's the importance of this? So I took a picture of this cannon over the summer because the cannonball was too big and it didn't go through, and it ended up backfiring on the guy who shot it. And that's what this is useful for. These are used for measurements only. They're not used for definitions or for, if you say, is the speed limit's 55, how many significant digits is that? That's just a rule. It's 55. It's an exact number. How many people are in a room? That's an exact number. Those are infinite significant figures. Significant figures or digits, as I sometimes say, are for measurements only. And they quantify the accuracy of a measurement. That's what they're useful for. So 0.1 centimeters is a different number than 0.100, because in 0.1, this is the number you estimated, but in 0.100, this is the one you estimated. So that means these two, are pretty accurate, the 0.1 and the first 0. That is the difference. And as I said here, so this cannonball, if you see here, was too big. So the guy might have said, I need a 9 centimeter diameter cannonball, but what he really needed was an 8.7 diameter cannonball, but he just rounded up to 9 because he didn't think it mattered. Well, it did, because 8.7 centimeter diameter cannonball would go through the cannon. A 9 centimeter or a 9.1, if he was rounding just to 9, would not. And that's why the issue happened. So significant figures are important for that reason. All right, so here are the rules for significant figures. We discussed that these rules can be summarized afterward with that picture of America, but any non-zero digit that is a measurement is always significant. So if you write down 8 centimeters or something, then that 8 is significant if you measured something to be 8 centimeters. Sandwich zeros are always significant. So here we have a non-zero number. Here we have a non-zero number. There's a 0 in between. So all 3 are significant. This has 3 significant figures. It has the 2 known and the 1 estimated. So that's a total of 3 sig figs. All right. And then I'm going to finish my F. All right. And then 3 leading zeros are never significant. So these zeros are just placeholders. So this is the same as 4 times 10 to the minus 4. And if we do it that way in scientific notation, my zeros are awful. If we do that in scientific notation, the beautiful thing about scientific notation is it shows all your significant figures right here at the beginning. So there they are. 4 is the significant figure. So we estimated that 4. So that's the last of the significant figures. That has 1 significant figure. But these zeros are just holding places. This is just letting us know that this 4 is in the, tens, hundreds, thousands, tens of thousands place. And interestingly enough, we talked about how in Puerto Rico there's a saying, eros un cero a lizquierda. That's not even close. Lizquierda. La izquierda. Sorry about that. It's not close, but we're going to keep going. And what it means is you are 0 to the left, which means you are useless. That's what it means. You're insignificant. So these zeros to the left are insignificant. Number 4, trailing zeros are sometimes significant. If you have a trailing 0 after a decimal point, then it's significant because you wouldn't have bothered to write it if you didn't measure to that point. Again, looking at this number, this is the estimated one, and these are the certain ones. So therefore, these are the certain ones. Pretend I didn't hit that last one. So you have 4 certain and 1 uncertain, 5 significant figures, but you did measure to this point. No, if there's not a decimal point. So 300, you estimated this 3. That's the only significant figure. So that only has 1 significant figure. All right. The last rule is conversions are considered infinite. So any definition, any conversion, anything that's exact numbered, like the number of people in the class, those have infinite significant figures. So a dozen equals 12. That doesn't have two significant figures because it's 12.0000 on. So it's considered an infinite significant figure because that's by definition. That 1,000 millimeters equal a meter. That 1,000 doesn't have four significant figures. It has infinite significant figures because it's a definition. That's the way it works. 1 inch equals 2.5 centimeters. That looks like it's only three significant figures, but it's not. It's infinite significant figures because it's a definition. So hopefully that makes some sense. And then this, I thought, was a great way to do it. So if you look at America, and we have the Pacific Ocean on the west coast and we have the Atlantic Ocean on the east coast, and you sort of think about if a decimal is present, so if the decimal is present, which starts with a P, then you start looking at the number from the Pacific side or from the left-hand side or the west side. And once you see a non-zero number, you start counting significant numbers. So that 1 is the first one, and that means this has a total of 4. 1, 2, 3, 4 significant figures. If the decimal is absent, A starts with Atlantic there, right? Absent, so no decimal. You start looking at the number from the right side or the Atlantic side, and again, you go over until you see your first non-zero number, and that's when you start checking off your significant digits. So 1, 2, 3, this has a total of 3 significant digits. And this Atlantic Pacific rule actually works really well for accounting for this. And so let's apply it to this number. So this number has a decimal. A decimal is present. So we're going to go with the Pacific side of things, which is west. And we just move over until we see the first non-zero number. And then we start checking them off. These are all significant. So that's 1, 2, 3, 4, 5, 6, 7, 8. And there's many less rules to remember now. You don't have to worry about the zeros that are sandwiched or whether it's a trailing zero or whatever. You just know that you're coming because there's a decimal place present. You come from the Pacific side or the left-hand side. The first non-zero number you do, you start counting. So this has 1, 2, 3, 4, 5, 6, 7, 8. That's 8 significant figures. That was a decent 8. All right, so we will stop there for now because that's all I got through in class. And I appreciate you listening and all that. And I hope you have a wonderful weekend. And I will talk to you when I get back.